A weak acid will only dissociate slightly in a solution, meaning that an equilibrium is established, such as the one shown here. We can then write an equilibrium law expression for our weak acid, otherwise known as an acid dissociation constant, or K subscript A. We write this the same way, products over reactants, so our products would be H3O plus times A minus, all divided by HA. We do not include the water because it is a liquid. If we have a large Ka value, it means that the reaction is favoring the products, meaning that we have a lot of dissociation, we would have a stronger acid. A small Ka value means we have a very weak acid. We can then calculate pH of a weak acid using our equilibrium concepts and our Ka values. In this example here, it's asking us for the pH of a 0.10 mole per decimeter cubed solution of ethanoic acid. Ethanoic acid is CH3COOH. If we react that with water, it is going to establish an equilibrium to form CH3COO minus plus H3O plus. Everything is aqueous except the water. Now, unlike strong acids, we can't just take the concentration we're given to figure out the hydronium ion concentration because it does not dissociate completely. Instead, we need to use an ice table to figure out the concentration of the hydronium ion and therefore figure out the pH. Initially, we start with 0.10 mole per decimeter cubed of our ethanoic acid. And we initially start with 0 of our conjugate base and our hydronium ion. Now, the only way for this equilibrium is to shift is to the right. So our changes are going to be negative x, and plus x, meaning that our equilibrium is 0.10 minus x, and x. We also are given a Ka value, and that is 1.8 times 10 to the minus 5. Now this is a very small number. If we were to apply our assumption like we did in our previous equilibrium problems, we would see that the initial concentration of ethanoic acid is much smaller than, our Ka is much smaller than our initial concentration of ethanoic acid, meaning that the initial concentration of ethanoic acid is going to be approximately the same as the equilibrium concentration of ethanoic acid. That means that we can leave that minus x out. That change is not significant, and we can make that assumption. If you are making that assumption, make sure you state so, similar to the equilibrium problems that we've done previously. Let's set up our Ka then. So that is going to be concentrations of our products over our reactants and then if we sub in our values, we would have x times x, or x squared, over 0.1, or 0.10. If we were to solve this then, x would be 1.34 times 10 to the negative 3. This is our hydronium ion concentration. So to get pH, we're going to plug this concentration into our pH equals negative log of H plus or H3O plus. And if we do that, we would get a pH of 2.87. We have a very similar situation when we have a weak base. A weak base will only dissociate slightly. Again, an equilibrium is established. We can write an equilibrium law expression for this reaction, and that is known as the base dissociation constant, or K subscript B. This is defined as the concentration of our products, our OH minus and our HB plus, divided by reactants, which is just B. Again, we don't include the water because it isn't in liquid state. Similar to acids, a large Kb means a strong base. A small Kb means a weak base. This problem here then can be worked very similarly to the previous problem, except now we're going to use a Kb value instead of a Ka value. I'd like you to try this one, so I will give you the reaction. It's hydrazine with water is going to establish equilibrium to form N2 H5 plus OH minus, where everything is aqueous except the water. Give that one a try. The last thing we need to talk about in this video is the relationship between Ka and Kb. If we take Ka and multiply it by Kb, they equal to Kw. If we are given then a Ka, we can figure out a Kb and vice versa. For example, calculate the Kb of Cn minus if the Ka for HCN is 6.2 times 10 to the minus 10. All we are going to do is plug those numbers that we know into the above equation. So we're trying to find Kb, and we know Kw, it's always 1.0 times 10 to the negative 14. If we solve for Kb, that is going to give us a Kb of 1.6 times 10 to the negative 5. We can also talk about pKa and pKb. So they are defined very similarly to pH, pOH, and pKw, where they are the negative log of either the Ka or the Kb. The larger the Ka value, it means a stronger acid, and it means that we're going to have a lower pKa value. The same happens with pKb. In your data booklet, you are given both pKa and pKb values for organic compounds, and they are found on page 13. Also similar to the pH and pOH, if we take pKa and add it to pKb, they equal pKw, or they're going to be equal to 14.